We have seen the cyclohexanone ring and to the carbonyl carbon at the alpha position. If there are polar group such as halogens is present, the which conformation is stable, whether acyl halogen is stable to the carbonyl group or whether equatorial halogen is stable which is present at the alpha position to the carbonyl function in a cyclohexanone. Okay, that is our cyclohexanone, and to alpha position. Okay, next to this position is the alpha, is there polar group is present. Okay, if it is present at the acyl one, or it may be present at the equatorial one. Okay, polar means it is having the lone pairs. Okay, lone pair is there, and oxygen also two lone pair is there. Okay, the such groups like the polar groups are the halogens. Okay, in this compound we have seen that there is a dipole interaction present in a equatorial polar group with the carbonyl group. Okay, this is our carbonyl group, and this halogen is the away from this oxygen, therefore there is no such dipole interaction or interelectronic repulsion or dipole repulsion. Okay, first thing we have clear that if the halogens is present alpha position to this carbonyl, next to this position carbon is the alpha position. If polar group is present, then if polar group is present at equatorial to the next to the carbonyl group, then this carbonyl group and the polar groups nearly eclipsed to each other. Okay, we have seen in previous lecture, that is if you see that carbonyl group is looking like that. Okay, like that way, and behind our halogen is looking halogen is nearly eclipsed to the carbonyl group. Okay, like that way, that X is, we can show. Okay, X is at equatorial position, and that, okay, like that way there are the groups. Okay, these groups we shown like that, and that hydrogen is like that. Okay, therefore this X and carbonyl nearly eclipse to each other, therefore the lone pairs of halogens or the polar groups and lone pair of the oxygen, there will be dipole repulsion is there, or interelectronic repulsion is seen there. Okay, in this case, in both these two cases, there are the interaction or the some instability is there. Okay, in this group we have discussed that the lone pair repulsion is there, that is the dipole repulsion is there, or interelectronic repulsion is there. Therefore it's that particular repulsion, dipole repulsion or the interelectronic repulsion produces some instability in the molecule. Okay, in this molecule Your polar group is or halogen is at the acyl one, therefore it also produces 1, 2, 3. 1, 2, 3. Okay, this interaction is there. 1, 3 diaxyl interaction. Is there, and therefore it gets the instability. Okay, amongst these two molecules or amongst these two conformation, which is most stable? This conformation found most stable conformation. Okay, therefore it is also get stabilized by the dipole-dipole interaction, or this is also unstabilized. This is unstabilized by this dipole-dipole interaction, and this unstabilized by the 1,3 diaxyl interaction, which is present in between the hydrogens and our polar groups, that is the halogens. Okay, therefore this conformation found is more stable and its quantity is higher. Therefore, by comparing these two things, one conclusion we have found that is the 1,3 diaxyl interaction is less than the equatorial interaction. Therefore, due to this molecule is found in higher in quantity or large in quantity. Therefore, this molecule mostly found in this conformation where polar group at the acyl position. Okay, such polar group is present to alpha position to the carbonyl group. That is, if you take the chlorine, if there, then it produces some peculiarities or some changes in properties or some changes in the values of or the peculiarities IR and the UV spectroscopy. Some peculiarities produced in IR and in UV spectroscopy, that is their value changes less or more due to this polar group is present at the alpha position to the carbonyl group in a cyclohexanone. Okay, when we have the halogen groups, suppose okay, that if suppose we take the halogen, if suppose chlorine is there, and in other case at the equatorial position, it is found that its IR frequency increases about 20 centimeter inverse, and this IR frequency for these carbonyls is normal. It shows the normal carbonyl frequency. Okay, normal carbonyl frequency is 1720 to the 1725 centimeter inverse. Okay, in this case it's going to increase the 20 units more. Okay, it shows the 1740 centimeter inverse IR frequency. Okay, therefore in this case you found that the carbonyl stretching frequency increases. Why this happens? We have seen that there is a dipole-dipole interaction is there. Correct? This equatorial and the carbonyl groups nearly eclipse to each other. Therefore, the lone pair of this chlorine and the lone pair of this oxygen, there is a repulsion is there. Okay, therefore due to this repulsion, this oxygen is try to repel from the chlorine. Okay, you know that if the double bond character of any functional group increases, if carbon is there, its double bond character is increases, then it increases the IR frequency. Okay, more stretching in frequency is required, more energy required to vibrate this double bond. Okay, as the double bond character increases, frequency is the higher frequency will increases. Okay, if suppose we have the such kind of unsaturation there. Therefore, the by the resonance, you will get the another such enol type. Okay, the keto and the enol. Okay, in this case, the character of double bond it decreases. Okay, due to this, you can show like that. Resonance is there. Okay, like that resonance you can see in this case. Therefore, double bond character for this carbonyl decreases. Therefore, higher frequency for this carbonyl also decreases. If double bond character increases, then higher frequency also increases. Okay, due to this repulsion, these electrons will pull by that carbon. Okay, due to repulsion, these electrons from the oxygen get pulled by this carbon, and due to repulsion, these two groups are the out of plane and try to out of plane, because it is then it's therefore it's get compressed. Okay, therefore by pulling that, by repelling this carbon will get compressed, and electron is transferred to this carbon. So due to this compression, okay, group is compressed or double bond is compressed, it means the its strength is increases. Okay, double bond character is increases. Due to this carbonyl frequency, double bond character is increases, somehow increases, and therefore it shows the increase in IR frequency by 20 unit than the normal IR frequency. Okay, in this molecule the chlorine is away from this oxygen, therefore such kind of compression is not possible. But in this case repulsion is there, therefore oxygen, carbon and oxygen compress for avoiding this repulsion. Therefore due to this the double bond character carbonyl increases, and carbonyl increases its stretching frequency, more energy required. Bond is strength of bond increases, it requires for vibration higher energy. Okay, as like if you pull the 50 kilo weight and if you pull the 100 kilo weight, okay, 50 kilo weight if you can easily pull, but 100 kilogram weight it is difficult to pull. Okay, therefore like that the strength of bond is increases, it is difficult to vibrate. Okay, as the strength of increases, bond increases, double bond character is increases, therefore it is difficult to vibrate, therefore for the vibration more energy is required, and therefore it absorbs 20 unit more than the normal ketone frequency. Okay, in this case no repulsion is there, therefore it appears, its frequencies appear normal 720 or 725 centimeter inverse higher frequency. Okay, there is no compression takes place because there is no repulsion is there. In this case repulsion is there, carbon will get compressed, somehow compressed, and its energy, its double bond character increases, its strength is increases, therefore higher frequency is required for the vibration. That's why it appears at the higher frequency. Okay, this is all about this. Okay, this peculiarity is found in the higher frequency when chlorine is axial or at the equatorial position. If also there is a changes in UV or lambda max. Okay, if you have the unsaturation, conjugation is increases, then lambda max is also increases. Okay, if your halogen group, okay, chlorine is there, if X is, we give the X is there, and in this case equatorial X is there. In this case the lambda max normally increase for this than the lambda max of the group is present at the equatorial. Okay, in this case the pi electron of the double bond of carbonyl, this is a pi electron, double bond is there, is a pi electron of carbonyl group, and this, okay, that is your chlorine is there, that is sigma bond of chlorine and the pi bond of the carbonyl groups can be easily overlap. Okay, this can be easily overlap. Okay, in this case it is not possible. The sigma bonds of these groups are not parallel to this pi bond of carbonyl group. Okay, in this case the pi bond of the carbonyl group is the can be overlap with the sigma bond of chlorine. Okay, as orbital overlapping higher, then lower energy required, and hence it absorbed at the higher lambda max. Higher lambda max means the lower energy. Okay, if such kind of higher overlapping orbital is possible in a molecule, then its lambda max increases. Such situation is not present if your halogen group is at equatorial. Therefore lambda max is increases due to the higher orbital overlapping. Okay, pi bond of the carbonyl and the sigma bond of the chlorine, they are the oriented in the same direction, they are the parallel. Therefore higher orbital overlapping is possible, and higher orbital overlapping means the lambda max increases and energy is decreases. Okay, that's why the lambda max is increases when your chlorine group or the polar group is at equatorial at axial, then lambda max get increases. Okay, this is all about the some peculiarities observed when polar group is present at equatorial or at the axial position. Okay, when in higher frequency is increases for when your halogen group is present at the equatorial one, and lambda max is increases when your polar group or halogen group is present at the axial one. Okay, this is all about the peculiarities occurred due to the halogen groups is present alpha to the carbonyl group. Okay, now enolization in a cyclohexanone. Okay, we have the cyclohexanone. Okay, we can draw the cyclohexanone is there, and enolization is takes place. Enolization means that is a keto form, and after enolization you will get the enol form. Okay, this will be your the enol form one. Okay, that is one of the hydrogen is there. Okay, in enolization it can be possible equatorial hydrogen can be removed or the axial hydrogen can be removed. Okay, both hydrogens can give the enolization, but deuterium experiment prove that mostly or majority axial hydrogen is pick up for the enolization, not the equatorial hydrogen is the pick up for the enolization. Okay, if instead of we put deuterium is here and the hydrogen is there, by the deuterium experiment you can found that the deuterium is remains in the compounds in enol compound, that hence it proves that the axial hydrogen is mostly pick up for the formation of the enolization in a cyclohexanone. Okay, why this is happened? This is happened due to there is some stereoelectronic requirement is there, and this requirement we can understand by observing the orbitals of the axial hydrogen and the orbitals of the carbonyl pi bonds. Okay, okay. Therefore, first observation we show that or seen that the acyl hydrogen is mostly abstracted or removed, or used for the enolization. Okay, in enolization mostly acyl hydrogen is used. Okay, first thing. Why this is happen? Okay, therefore we have the pi bond for the carbonyl group is there, and at the acyl one, the acyl hydrogen, this also the pi bond is there. Oh, sorry, sigma bond. Okay, therefore the if it loses, okay, it gives the which is lone pair. Okay, in this case, the sigma bond of hydrogen, acyl hydrogen, remember that, sigma bond of acyl hydrogen and the pi bond of carbonyl group are parallel to each other in one direction, and therefore it can be easily overlapped during the formation of the enolization. Okay, therefore these pi sigma electrons of the hydrogen and the pi electrons of the carbonyl functionality, they are easily overlapped during the enolization. Okay, after the losing the hydrogen, that is negative charge is there. Okay, that is shown by this lone pair. In this case also you have the like that, there is a overlapping is there. Okay, therefore this strongly it use the acyl hydrogen during the enolization. Okay, if you do the attack of the H plus ion, then its H plus ions attack is also takes place from the acyl side. Okay, this H plus, after the addition to this enolate, it also gives the acyl hydrogen. Okay, like that. Because why it gives the acyl hydrogen? Okay, due to we are enolate is like that. Okay, double bond is there. Okay, like that you will obtain this hydrogen. It is the H plus is also acyl, because after this you will obtain this kind of situation. Okay, CO. Okay, that is double bond, pi bond is there, and if you add the hydrogen, therefore these acyl negative charge, okay, at that situation, that acyl orbitals and the pi orbitals are the parallel and they can be easily overlap. Then therefore it can, when attack on the H plus ion or any cation, the cation will be attacked from the acyl position and it will be takes the acyl position when you add the H plus ions. Okay, therefore enolization takes place from the acyl side. I hope today you will get all these idea. Thank you very much.